Okay, so let's generalize the discussion that we've been having about, in particular, the differential equation, the system of differential equations for the pendulum. So let's just consider some autonomous, okay, and so what we mean by autonomous is these differential equations don't depend on time. And we might have some situations where they also depend on time. But the rate of change of x and y are two dependent variables. They just depend on the dependent variables x and y. This one is nonlinear because we have this x squared term here, and we also have this constant term over here. So by linear, we meant that it could be written as dx dt is ax plus by, dy dt was cx plus dy. So now this is nonlinear. This part over here is linear, but the first equation is nonlinear. We have a squared term here, and we have a constant over here, which we also shouldn't have for a linear system. So we've already thought about analyzing these systems to some extent. We've talked about how we can find the phase plane equation and in some situations solve those phase plane equations. We've also talked about how we can find equilibrium for these systems. So in this case, if we wanted to find the equilibrium, then I would set this equal to 0 and this equal to 0, and then try and figure out what coordinates x, y would simultaneously make those equations equal to 0. And you can quickly verify that this system has exactly two equilibria, one at 1 minus 1 and the other at minus 1, 1. Okay, and it makes sense that from the top equation, we see that x has to be either 1 or minus 1 for this one to be equal to 0. And then that would imply, coming down into the bottom equation, that y has to have the exact opposite sign of x. So that's where these two equilibrium come from. And so now the question is, well, how can we determine whether those equilibrium are stable or unstable? For the case of linear systems, what we were able to do was, well, those systems only had one equilibrium, first of all, which was the origin. And then we took a look at the corresponding matrix of coefficients of the linear system of equations and found the eigenvalues for those systems. And those eigenvalues told us something about the stability of the equilibrium at the origin for a linear system. So what's nice, you can relax, we're going to do all of the same exact stuff to look at the stability for nonlinear systems. So we're just going to take all of the techniques that we've been looking at and apply them to a different scenario. So in order to do that, we're going to have to extend this idea of linearizing equations. So earlier we took a look at the function sine theta, and we said, okay, if theta is close to 0, then we can find the tangent line for that graph at 0, and that's going to give us a good approximation for the function. Here are equations for dx dt and dy dt. These are functions of two variables. So in order to linearize each of these equations, we're going to need to do a little bit of multivariable calculus. So what you may not recall, but if you don't, that's okay. We're going to review it right now, is that we can similarly linearize functions of two variables or even more variables than that. So if you're dealing with a function, say like z is some function of x and y, then from your multivariable days, you might remember that this could be some surface over here. And what it means to linearize this equation means that we can approximate that curved surface with a tangent plane. Okay, so that's kind of the picture about what you did in linear algebra. But how that works is pretty similar to how we find tangent lines. And so the linearization for a function of two variables we get by first evaluating the function itself at that point. So that's this piece over here. Then we calculate the partial derivative of that function with respect to x at the point where we're doing this linearization, and then we multiply that by x minus x0. And then we do the same with respect to y. Find the partial with respect to y, and then we multiply that times y minus y0. And so that's what we would call the linearization for f of x. Keep in mind, you could go further. You could find the quadratic approximation for it and so on. So we're going to use this idea from multivariable calculus as a way of linearizing these equations up here in particular, which is a nonlinear equation. And so to make this equation a little bit simpler, I'm going to introduce a change of variables. I'm going to introduce a new variable u, which is equal to x minus x0. And all that's going to allow me to do is take this piece over here, instead just call it u. And I'm going to introduce a second variable v, which is equal to y minus y0. So that means I could take this piece over here and just replace it with v. And so now I can think of this linearization as a function of our two new variables u and v. Since this is going to be a constant, when we evaluate the function at a particular point, we're going to get a constant. The derivatives are going to give me constant values. So what's going to be left is going to be some linear equation in terms of these new variables u and v. And this is what we're calling the linearization. So how you can think about this variable u is this is telling us how far away are we from x0. And you can think about v as being like dy. It's telling us how far away have we moved in the y direction from the value y0. Okay, so where we're going to do this linearization is going to be at the equilibrium points. So let's take a look on the next slide about what the linearization would look like for each of these functions, say at the equilibrium 1 minus 1.